Okay, so we're going to look at a lot of different types of polar equations, some basic ones to start, some circles, some lines, and then we're going to get into some really unique ones after that, all right? So let's start here. Convert each polar equation to rectangular form and then graph. All right, this first one's really easy. R equals 4. If I square both sides, I end up with r squared equals 16. And then I can convert r squared to x squared plus y squared. And what do I have there? That is an equation of a circle. What's its center? It is the origin. And its radius is 4. So does that make sense in polar form? We'd call that r equals 4. All right, so in the grid there, it's the fourth circle, the fourth concentric circle of the grid. Okay, so it's this. Just do your best here to draw that out. So if all I see is r equals a constant, it's always going to be a circle centered at the pole. Okay. All right, pick a different color. Theta equals pi over 4. To convert this to rectangular form, I'm going to use tangent on both sides. Okay. What's the ratio for tangent? Y over x, yeah. Oh, there we go. We're in rectangular form on that side. And what's tangent of pi over 4? Just 1, right? Multiply both sides by x to clear the fraction. Y equals x. Okay, isn't that the equation of a line? With a slope of 1. And its y-intercept would be 0, meaning it passes through the origin, or in this case, the pole. Okay? Now, the polar grid is made up of circles and lines, right? And each of those lines, doesn't it represent the terminal side of an angle? Okay, so right here is 0. Then it goes pi over 12, pi over 6. Next is, this one's pi over 4 right here. So here's the complete line for pi over 4. Now, a misconception some students will give, a lot of times I'll see them only draw from the pole up, like we're only working in the first quadrant, okay? Because if you look at a labeled polar grid, this side of the line would be labeled with 5 pi over 4, right? Not pi over 4. So sometimes students think, oh, I shouldn't include that half of the line. But think about how we plot points. If I had negative 2 pi over 4, what would I do? I would rotate to pi over 4, and I would go 2 back, okay? Which would end up on that half of the line, okay? All right, pick another color. R equals 2 over sine. I could just multiply both sides by r there, or I'm sorry, by sine. I end up with r sine theta equals 2. Well, what's r sine theta? Isn't that y? What does y equals 2 represent? If I were to graph that. Yeah, that's a horizontal line. Okay, so how would I graph a horizontal line in the polar grid like this? Well, that circle of radius 2, right there, it would intersect the y-axis at the point 0, 2, right? And this horizontal line should pass through that. And the way it's going to look, it's got to be tangent to that circle. It's got to be a tangent line. That is not a very straight line. Let's try that again. What if I had r equals 2 over cosine theta? What would the graph look like? It would be vertical, right? It would be x equals 2 in that case. Okay, pick one more color. All right, now this one's going to be probably the most involved. We actually had one like this in our notes at the end yesterday. So r equals -2 cosine theta. I'm going to multiply both sides by r this time. That'll create r squared. And then over here, -2 r cosine theta. R squared can convert to x squared plus y squared. And then -2r cosine, isn't that -2x? Anybody remember from yesterday what we did at this point? Yeah, we ended up completing the square. So to do that, I'm going to have to add the 2x over, group those together. One completes the square, right? I end up with x plus 1 squared added with y squared, that equals 1. So that is the equation of a circle, but this time the center has moved, right? The center is now at the rectangular point of -1, 0, and the radius is 1. Okay, now to graph that, we can plot the center pretty easily. Right here would be -1, 0. Radius of 1 means we'd have a point over at the pole, and then over here on, that would be at 180. So I go 1 right and I go 1 left from the center. Now, it's hard to figure out how do you go 1 up and 1 down in this grid system, right? So maybe what we want to do at this point is plug some values in for theta to get some r values. Okay, so based on where this circle is ending up, I think 3 pi over 4 would be a good choice, or that's 135 degrees. And I think 5 pi over 4 could be a good choice. Okay, so we pull out the calculator. I make sure I'm in radian mode here. So I'm going to do -2 cosine 3 pi over 4. And just get an approximation for that. Okay, it ends up just being radical 2, right? Because 3 pi over cosine of 3 pi over 4 would be negative radical 2 over 2. Multiply it by the -2, you get positive radical 2, which is approximately 1.41. Okay, change it to 5 pi over 4. See how you get the same thing? Okay, so where would those points plot? Well, right here is 5 pi over 4. So we have to approximate where 1.41 would be on that. Right about there. And then right here would be 1.415 pi over 4. Now we can give a pretty reasonable sketch of the circle. Did I have to use 3 pi over 4 and 5 pi over 4? Could I use other angles in quadrant 2 or quadrant 3? Absolutely. The more angles you plug in, the better. Questions on any of those examples? All right, so now let's get into the very unique graphs, cardioids and limasones. Okay, so all of the equations we're going to look at in the next few examples, their equations will follow the format. You'll have a number, A, we're calling it, added or subtracted with another number, B, that's either multiplying sine or cosine. Okay? If you have sine in the equation, there's going to be some symmetry always with the graph that can help us in finding points, okay? So think, for the sine function, you are positive in quadrants 1 and 2. You're negative in both 3 and 4, right? Isn't that symmetry over the y-axis? Or we're going to call it over the line theta equals pi over 2, which coincides with the y-axis. There's symmetry here. Okay, now what about cosine? Cosine is positive in 1, negative in 2, negative in 3, positive in 4. Where's the symmetry? With the x-axis. Or in the polar form, we're going to say with theta equals 0. Okay, so that's the first takeaway. Now, the second takeaway is based off of how the values of A and B relate to one another. If A and B are the same, if those numbers are equivalent, you're going to get what we call a cardioid. And the reason we call it a cardioid, it resembles a heart, okay? If A is greater than B, so the number out in front, if the number that's being added or subtracted is larger than the B value, then you get a limasone that does not have a loop, which that'll make more sense here in a moment. Okay, and when you're working with that type of graph, it's not going to pass through the pole. It's not going to have a point at the origin. If you switch it and you make A less than B, then you are going to get a limasone that has an inner loop, and it results in a graph that passes through the pole twice. Okay, so let's look at a couple examples here. I'm going to use this illustration. Okay, so let's say let's do 2 plus 2 cosine of, I have to use a t here because this applet is using a parametric function, which we'll learn hopefully more about those later in the course. Think t right now, think it's theta, it's our angle, okay? All right, now I'm going to hit graph, and you're going to see this sketch out starting at an angle of 0 all the way to an angle of 2 pi or 360. Okay? Speed it up a little bit. Okay, so it's going to come into the pole, and then it's going to bump back out, and there we finish off. So this is called a cardioid, okay? Loosely resembles a heart, yes? Okay. And again, notice this is cosine in the equation. I've got symmetry with the polar axis here with theta equals 0, okay? I got a cardioid because A and B were the same. All right, now, had I changed this to 2 plus 2 sine of t. Okay, let's start over. speed it up a little bit. It's going to look like the same graph just been rotated to where we now have symmetry with the y-axis, or with theta equals pi over 2. Okay, let's pause that, erase. Let's say I change this to 3 plus 2 sine t. So now A is larger than B. Now we're not going to reach the pole. Since A was larger than B, the distance between the pole and, we call this the dimple of the limacon, is 1 unit. It's the difference of A and B. Okay? All right, and then let's say we switch it. Pause, reset. Let's go 2 plus 3. These are the fun ones. This is the limacon with a loop. Okay, watch this. Passes through the pole, loops around, passes through the pole again. Okay. Again, loops around, passes through the pole a second time. All right, so let's go to the notes. I've got a couple different examples prepared of these. Okay, so let's just do a cardioid first. Okay, so how do I know it's a cardioid? A and B are the same value. I see cosine in there. I know I have symmetry with theta equals 0, or the polar axis. So I'm going to draw that in. Okay, and then I'm just going to make a big long table of values here and plug some different angles in for theta. Okay, I'm going to start with 0. So that would be 2 plus 2 times cosine of 0, which is 1. 2 plus 2 times 1 is going to give me 4. So that would plot right there. Okay, then I'm going to jump to pi over 6. 2 plus 2 times cosine of pi over 6. Well, cosine of pi over 6 is radical 3 over 2, right? So those 2's are going to wipe out. You'll end up with 2 plus radical 3, which you'll have to approximate that. That's 3.7. Okay, so we'll rotate to pi over 6, and we'll move from the pole along the terminal side, 1, 2, 3.7. Just estimate it. Let's do pi over 4 next. That's 2 plus 2 times radical 2 over 2, which will simplify to 2 plus radical 2. That's approximately 3.41. Right about there. Then I'll jump to pi over 6. Or I'm sorry, pi over 3. Or did pi over 6. That's 2 plus 2 times 1/2. Cosine of pi over 3 is 1/2. So that one's going to work out nicely to give me exactly 3. So right there would be 3 pi over 3. Okay, and then I'm going to go up to pi over 2. That's going to be 2 plus 2 times 0. Cosine of pi over 2 is 0. So I end up with a 2. All right, there's my point. Oops. Okay, so I've used a bunch of first quadrant angles. Now let's use some second quadrant angles. Okay, about 2 pi over 3. That's going to give me 2 plus 2 times negative 1/2, which will end up giving me exactly 1. Okay, so right there is 1 2 pi over 3. How about 3 pi over 4 next. That's going to give me 2 plus 2 times negative radical 2 over 2, which is approximately 0.6. So that's going to plot right there. Okay, and then let's do 2 more. 5 pi over 6, or 150 degrees. Cosine there is negative radical 3 over 2. That's going to approximate to 0.3. See how we're getting close to the pole? Just do your best to plot that. The last value I'm going to use is pi. 2 plus 2 times negative 1. Cosine of pi is negative 1. That's going to give me exactly 0 and put me right at the pole. Okay, now I could plug in values for third and fourth quadrant, but here's where I'm going to use my symmetry knowledge. I'm going to take all those points I plotted and reflect them over the polar axis to get more points. And now I can draw this out. Just do your best with it. Draw it slowly. So this is how it would trace out from start to finish, as we saw in the applet.